All right, can you guys hear me okay though? Because I have my sound off on this computer and I have it on this one. Can you guys hear me okay? I see thumbs. Yes.
Yeah, we can hear you.
Okay, good. All right, so on Tuesday, remember we just kind of talked about kinematics. So we were saying we hadn't really talked about what kinematics were. Jordan, you can't hear me? Like I need to talk louder, or you can put it in the chat if you need to. Can you hear me at all? Do I just sound muffled? I don't know if he's typing. Can anybody see in the chat what he said? He just said I can't hear you, right? Wait, is he still on? He's still on here though. Okay. All right, I'll try to talk louder. Okay, so let me. All right. So on Tuesday, we talked about kinematics, and we really didn't say what kinematics were, but anybody remember what we were talking about? On Tuesday, we were talking about two very adventurous ideas or concepts or activities. Anybody remember what one of them was? Nobody remembers what we were talking about? And I took a poll and said, would you do this one, or would you do both, or do neither? And I said, I'm not doing either one of them.
Skydiving, free falling.
Yeah, skydiving and base jumping. So we were talking about, that's what we were talking about on Tuesday. And we were going to eventually connect it to everything else. So let me just make this a little bit bigger. All right. So there we go. We were talking about skydiving and base jumping. We kind of went through this. We talked about the difference. We watched some videos on it. This was base jumping. They like run and jump off the top of a building or off a cliff or whatever. Skydiving, they're actually jumping out of the plane. And then we talked about whether the person was falling with a constant velocity or whether they were accelerating, which means that they are speeding up. And Parker, which one were they doing? Were they accelerating or were they falling at a constant velocity?
They were accelerating.
Correct. Good. So they were accelerating. All right. So then we looked at a video of someone dropping a ball. And then when we could look at the final picture, because they were taking pictures as the ball fell, we could see like here, okay, like you could see the ball, like these lines were evenly spaced apart. And as you got further down, you see like the ball would like skip a whole, I think it was like a quarter of a meter, so like 0.25 meters. So here you could see the ball, and this is falling. So you could tell it was accelerating because it got to the point where it was skipping a whole 0.25 meters before you saw the ball again. All right. So then we talked about what would happen if you let go of your phone. We talked about being called free fall motion or free fall. And it's just saying that there's nothing acting on it but gravity. And we said gravity, Faith, which way did we say gravity pulls you? Up, down, left, or right? Faith. Faith Johnson. Which way does gravity pull you? Down, left, or right?
Down.
Yes, gravity pulls you down. Okay. So then did we finish this video? Because in one of my classes we didn't finish it. Did we finish this?
No, you decided to leave us at a cliffhanger.
Ah, I left you on the cliffhanger. Oh, okay. Anyway, so yeah. All right, so let's they were getting ready to drop it, right? Is that what they were about to do? Somebody tell me, is that what they were gonna do? About to drop it?
Yep.
All right, so let's see if we can watch it. I may have to use my audio here. Let's see. Tell me, guys, if you can hear it.
This is NASA's space power facility.
Can you guys hear that?
I can hear it.
Video isn't showing.
I should probably share. I know I'm looking at the screen. I know I'm not sharing, and I still did it. So it has captions if you want to read, but tell me if you can
The
hear it.
world's biggest vacuum chamber. It's used to test
You guys
space
can't hear that, can you?
conditions in outer space. And it does that by pumping out 30 tons
no.
of air in this chamber until there are about 2 grams left.
Can you guys hear it?
And it's kind
Okay.
of an eccentric construction of its history. It was built in the 1960s as a nuclear test facility to test.
All right, so he's talking about all this stuff with this building that they built. That's basically what he's talking about. I'm gonna skip forward a little bit because we said we were at the point where it was about to fall. So let me just do this. Let's see. We got to the point right here. Here's the crane with the bowling ball and the feather.
Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case,
Now, a lot of people said that they thought the bowling ball would hit first. So I guess you were right, but let's keep watching.
feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air.
Okay, so in case you didn't hear what he said, now to see how that would look if only, sorry, I have to hear something in both. If only gravity is acting on it, now they're gonna suck all of the air out of that building. Okay, so they're gonna make it it's called a vacuum. They're gonna suck all of the air out of the building and they're gonna do it again. So that's what they're getting ready to do right now.
It takes 3 hours to pump out the 800,000 cubic feet of air in the chamber. Drop 2 millitorn and last 30 minutes. Once it's complete, there's a near perfect vacuum inside. 60 millitorn air station 1. 30 days, 1 pressure set point, 40 psi. Very low drop. 5, 4, 3, 2, 1, release. Look at that. They came down backwards. Wow. Exactly that goes silent. Exactly the same. Feathers don't move, nothing. That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down, gravity. But Einstein imagined a scene very differently. The happiest thought of his life was this. The reason the bowling ball and feather fall together is because they're not falling. They're standing still. There is no force acting on them at all. He reasoned that if you couldn't see the background, there'd be no way of knowing the ball and the feathers were being accelerated towards the earth. So he concluded they weren't.
All right, so once they removed the air from there, okay, the force of air resistance, then all they had acting on it was gravity. So I had a lot of people, no one told me the feathers would hit first, so that's good. Everyone either said the bowling ball and the feathers would hit at the same time, so you're technically right, or the bowling ball would hit first, also right. So it's a matter of, are there other forces acting on it? If it's only gravity acting on it, then the bowling ball and the feathers will hit at the same time. The air resistance was what was keeping the feathers from falling at the same rate as the bowling ball. All right, here we go. So now, okay, here is a new number that we are going to become very familiar with. It's called the acceleration of gravity, okay? And here's the thing that was weird. So remember we talked about, we said it's an acceleration. I asked you, was it positive or negative? And what did we think it should be? If things are falling down, okay, like the ball or the bowling ball, and it was speeding up, we said, what do you think the acceleration would be? Would it be positive or negative?
Negative.
We said it was going to be negative. So in our mind, we wanted to believe initially, remember I asked everyone in the chat, everybody said it's positive, okay? And it's like, why would it be a negative acceleration if it's speeding up? Because remember we said usually speeding up is positive and slowing down is negative. So why would the acceleration when things are going faster be negative? And the reason is because of the direction, okay? So the negative sign, okay, is telling us that it's accelerating, but it's accelerating down. So that's why we use a negative sign, okay? So just looking at this slide again, it says the acceleration at the Earth's surface is at a constant 9.8 meters per second squared toward the center of the Earth. And it says we're gonna, for our purposes, so basically we're gonna not think about air resistance, so the things that, you know, kind of slow things up or push them upward. And then it says small variations due to elevation and regional average, which just means, okay, if we're talking about gravity pulling you down and it's pulling to you towards the center of the Earth, well, if I'm at sea level versus a mountain, that number is just the tiniest bit different, okay? And this is gravity. I want to make a note. This is gravity on Earth, okay? So gravity on the moon or on other planets is a different number, okay? It's a different number. This is gravity on Earth. So it's negative 9, it's 9.8 meters per second. That is the acceleration. And the negative just says pulling us down, okay? So if you're going down, moving towards the center of the Earth, then it's negative. All right. So, oh, I just saw that. Okay. Here we go. All right. So now this is where we have the notes. So let me just show you where we are if you have your notes open. Okay. Let me 1 second here. All right. So if you are in the Schoology, okay, you're in Schoology, there's something here that says, this is the PowerPoint that I'm going through right now, and here's the notes. So if you click this, it's gonna open a Google Doc. And it's not, let me go over here and open mine, okay? And it looks like this for you guys, okay? So right here, you could potentially write in stuff, and everything that you would be writing in would be red. So for example, okay, when I go to, let me do new share, let me just do here, okay. So right here it says kinematic equations can only be used when we have constant acceleration, okay. And so when I go to my notes here, it says kinematic equations can only be used when we have, and I would put constant acceleration, okay? So if you can't access the notes, you may want to just write down the stuff in red on some paper, and we can go back and put them in later. Okay. All right, so I'm gonna go through the PowerPoint. I'm probably not gonna have the notes up, okay? But you can be filling in the stuff that's in red as we go, okay? And we hopefully will get to at least one practice problem. All right, so I'm gonna go back to the PowerPoint. I'm getting good at switching, look at that. All right, so kinematics, I know it sounds like a nice big fancy word, but don't worry about it. It's just saying, it's just another set of equations, and we use it when we have constant acceleration. Well, for the most part, when we have constant acceleration is when you have an object that is free falling, which just means I dropped it. Let's drop this instead. Okay, free falling is not levitating in air. It did not go any, it went straight down because gravity pulled it down. So any free falling object or projectiles, now projectiles are things that you shoot. So like a rocket or like a bullet out of a gun or a cannonball out of a cannon. Those are projectiles. And they tend to make, a lot of times they tend to make a shape like this. They kind of go like this. Okay. So even if a rocket, even if you shoot it up, it eventually comes back down. Okay, so that's a projectile. Right.
Miss Page,
Yes.
I'm not sure if you were showing something, but like, I only see the kinematic equation.
When I was talking about the projectiles, look at my camera. Sorry, let me show you again. Can you see me waving?
No.
You can't see me waving? Can anybody see me waving? Oh,
I can't see nobody.
you can't see anybody? Okay. Well, here, let me stop sharing so you can see me for a second then. I'll stop sharing just so you can see me for a second.
All right, now I can see y'all.
Can you see me now? All right. Lydia, can you see me? Lydia. Can you see me? Jalen, can you see me?
I can't see.
Yeah.
Who can't see me now? Kaylee, you can't see me now?
I can't see you.
All right, I'm gonna do it both ways. All right, if you can see me now, projectile usually makes this shape. If you're looking at me, goes up, comes back down, okay? Even if you shoot a rocket, so it's like an arch or arc, okay? So even if you shoot a rocket, it's gonna go up, but then it's eventually gonna come back down. So it's just a matter of an arc. And I'll do it again with my screen shared. Let me see if I can, write on this board over here. Give me 1 second. I'll try. Oh. All right, let's see if you guys can see this. I left my pencil. Oh, you're not gonna be able to see it because I'm sharing from this screen. But basically, it's like an arch. Oh, I'm struggling. Okay, it's an arch. We'll talk about. I'll show you guys in a second. I promise. We'll talk about it. I'll put this on the other screen in a second. All right. So we know that friction is like if we go like this is friction. Okay. So friction is anytime two things are in contact with each other. Anytime you have two things that are touching, there's friction. It may not be like us rubbing our hands together, but anytime two things are against each other, including us against air, there's friction. But in this case, we're not even gonna think about it. Like those feathers falling, that was friction between them. So we're not gonna think about that. So this just says all free falling objects or projectiles have a constant acceleration down. Okay. People still can't see me. So I'm moving my hands. Can you see me, Kaylee? You cannot see me. All right. I know what I'll do. Okay, let's do this. Fantastic. All right, so here we go. So yes, so the only time we can use kinematics, okay, is when we have, let me do a different color here, is when we have constant acceleration, except for erasing, constant acceleration, okay? And a projectile, aha, now we can do this. A projectile makes this shape. It kind of like shoots like this, and eventually it's gonna go down because guess what's pulling it down? Guess what's pulling it down? Very nice, gravity's pulling it down. So a projectile, even if we shoot a rocket ship, when we shoot rockets and they go straight up in the air, eventually they still have to come back down, okay? And that's because of gravity. Gravity pulls it down. All right. So this is the number we'll always use, this 9.81 meters per second squared. And we just put a negative sign because that tells us that it's going down, okay? All right. So now let's go to the next slide. Next slide. Oh, I guess I have to clear all that. All right, so here are our kinematics equations, okay? So our kinematic equations are, they look really difficult, and I know they kind of look kind of funky, but let's talk about, we've used a lot of these letters before, right? Like V, even if you didn't see it all the way down there, what did you think, what have we used V for before? What did it stand for before?
Velocity.
Yeah, it stood for velocity, and so it still does. So we have D for displacement, okay? You got a, oops. Let me go back and back. Wait, I'm going the wrong way, aren't I? Yes. All right, now I gotta do draw. All right, so we have D for displacement. All right, we talked about that before. That's just basically how far you move, okay? And then we have VI, which remember was initial velocity. Okay, and this is already in your notes, just so you know, okay, initial velocity, which is remember velocity is meters per second. So remember, initial just means where you start, okay? This is a plus sign, so this is a T. Now, what does this mean? So if this is VI, okay, and that's a number, and then we have T next to it, which represents time. What are we doing with these two numbers right here?
Is it initial velocity times most times time?
Yes, exactly. Okay. So when you see all those letters smushed together, that means we need to multiply them. Okay. And then so we have A, okay, which is right here. This is A. All right. And A is acceleration. Okay. And meters per second, acceleration. Sorry, I'm learning to write on this board, which is right here. All right. And then we have T again, which means we're going to multiply it again. Okay. And this T is squared. Who remembers your order of operations? Anybody know a shortcut?
Are you talking about PEMDAS?
Yes, it is PEMDAS or PEMDAS or whatever you would like to call it. So remember, please excuse my dear Aunt Sally, okay? Now these two together, this acceleration and this time, is just gonna be just like what Parker just said. We need to multiply those together, but multiplying is all the way down here. What is this E for?
Exponents.
Exponents. I guess I gotta call on people, no problem. I'll do that. Exponent, this is an exponent. So you have to do your exponent first. Let me make my thing bigger so I can see everyone. Very nice, Stephanie, thank you. Yes, it is exponent. So I have to do that first. So we're just kind of talking about how they will lay out, okay? And then we'll, oh my gosh, time just flew. All right, same thing over here. So this one is you got a final velocity and you square it, okay? And then that's equal to a initial velocity that's squared. And then we have here 2, so this is 2 times A times D, okay? So I know these equations look crazy, but at the end of the day, I'm going to give you almost every single piece except for one. So we just have to work backwards to find whichever one is missing. So we're probably not any practice problems today, but let's see what we're going to do. Okay. All right. So here's how we solve problems. Notice that these are in red. So that I'm getting there, guys. This
Are
way.
you okay?
Yes, I'm trying. I'm getting used to this board. It's just, it's a lot easier if, yes, I'm okay. All right. Everything that is in red is what you will fill in on your notes. So for instance, when we are solving problems, you will list all of your knowns and unknowns. What do I know? What don't I know? We've been doing that anyway, right? So when we used to do like speed equations and it was S is equal to D over T, we would write out S is equal to, D is equal to, T is equal to, and if we had a number for this and a number for this was the one that was missing. That's what this is saying. List your knowns and unknowns. All right, compare them. Then we're going to draw a diagram, plug them back in, and solve for the unknowns. I will work on my technology. We'll get it together. We will continue on Tuesday. Have a fantastic weekend. Goodbye. See ya.